Hello, Calculus. This video is going to cover section 4.3, Riemann sums and definite integrals. And here's the assignment. There's a handful of questions to be done, paper, pencil. And then we've got 1, 2, 3, 4, 5, 6, 7, 8 on your favorite website, WebAssign. Let's dive in. Section 4.3, we are going to understand the definition of a Riemann sum, evaluate a definite integral using limits, evaluate definite integrals using the properties of definite integrals. And then here they've added this in the new edition of the book. They put the trapezoidal rule in here. Historically, I've made trapezoidal rule a little like a subsection for extra credit. I'll talk more about that in class. So, in the definition of area we saw in the last section, the partitions have subintervals of equal width. This was only done to make our computations convenient and easy. The next example shows that it's not necessary to have every one of your rectangles equal width. Again, why should we make our computations easy and convenient? Why don't we make them as complicated as possible? And when we're going to find some area under a curve, it's real easy if all of your rectangles have the same base. What if we make every rectangle have a completely different size base? That'll make our computations incredibly hard, and we'll still get to the exact same answer when it's all said and done. So let's dive in with example 1. Consider a region bounded by the graph of the root of x and the x-axis between x is 0 and 1, as shown here in the figure. So here's our square rooting graph. The square root of 1 is 1, and we want to chop that up into some intervals. Actually infinitely many intervals at the end, and we're going to add them all up and get the exact value of area under the curve. And again, we could make it easy on ourselves and make every rectangle's base exactly the same, but what fun is easy math? We're going to make it a little harder by making every rectangle have a slightly different base. So here it is in its purest notational form. The limit as n goes to infinitely many rectangles. The summation of from the first to the nth rectangle. F of c sub I, that is the height of the rectangle. Delta x sub I is the base of the rectangle. Blah, blah, blah. C sub I is the right endpoint of the partition given by this. C sub I is I squared over n squared. Delta x sub I is the width of the ith interval on that width, or on that interval. So where do we begin? Well, they told us that c sub I is equal to I squared over n squared. I squared, ooh, this is, there we go, I squared over n squared. So delta x, the width of any rectangle's base, is going to be this endpoint, the right endpoint, I squared over n squared, minus the point that would be right next door. That's going to be quantity I minus 1 squared. Oh, this is going to drive me crazy. Over n squared. There it is. So this would be the right endpoint. This would be the left endpoint of any of our rectangles, and we're subtracting them. So this, it is a very complicated way to find the base, the delta x, of any of our rectangles. If we want the base of rectangle number 4, we would plug in 4 for the i's and compute that, and we would have the width of that rectangle. Now, trust me on this algebra, just to save us a little time and a whole bunch of writing. We want to get I squared over n squared minus this to be one fraction. Our common denominator is already there. It's going to be n squared. If we FOIL this out and distribute the negative and combine like terms, our numerator is going to be 2i minus 1. And that is over n squared. So that is our delta x, the base of any of our rectangles. Again, we would plug in n would be the number of rectangles we want. Eventually, we will let n go to infinity. I is the number identifying that rectangle. Okay. So let's see here. Let's get in our limit notation. Our limit, n will eventually be head off to infinity. Now, I'm not going to, this right here, we're going to start subbing some stuff in. This limit as n goes to infinity. We've got our summation symbol comes next. The summation from I equals the first rectangle to the nth. Here is f of c sub I. This is the height of our function, and we are dealing with the square root function here, so we're going to do the root of, and what goes in there is the I squared over n squared, our c sub I from right here. So that's going to be I squared over n squared. So that is the height of the rectangle, and then we got to multiply that by the width, or the base, and that is this, 2i minus 1 over n squared. And I think I can get rid of this now. So here is our equation, or our it's everything's thrown into the function. We have our rooting function. Here is the height. Here is the base of our rectangle. Okay, now let's see what we can do with this algebraically. N goes to n. I'm going to leave a little gap here between the limit notation and my summation. 1 to n. Now let's see here. I squared over n squared, and they are under a radical. Those are the only terms. So that will become an I over an n. And then we're going to multiply that by 2i minus 1 over n squared. So now we can pull things out in front of the summation symbol. Remember, we have formulas for the i's. We have the summation formulas for I, so the n's and any multiplied numbers can be pulled outside. So here is our summation again from 1 to n. So we've got an n, and it's going to multiply by this n squared, and when it comes out, it will stay as a denominator. So that is 1 over n cubed. And then we've got our summation symbol, and let's see what we're left with. Let me switch to red ink. We've got this I times quantity, 2i minus 1. Let's distribute the I. So that's going to be 2i squared minus I. And let's see here. I'm debating, should we distribute the summation and the 1 over n cubed, or should we save that more toward the end? Yeah, let's save it for the end. So limit, n is heading off to infinity. We have 1 over n cubed. Now let's see here. We're going to use our summation formulas and do all this at the same time. So I'm going to block this off in black ink. We have the summation of 2i squared. And that is going to be replaced with 2 times, now I'm going to switch to blue ink and do the I squared formula. So the 2 come down, and now we've got I squared, and I squared is n times n plus 1 times 2n plus 1, and that is all divided by 6. That's right, 6. So that's our first part there. That's summation. And then we've got minus. Here's I. And we've got a formula for I. That's n times n plus 1 all over 2. Close the brackets. Remember, this 1 over n cubed would be distributed to both of those terms. So now it's just a whole bunch of algebraic simplification. And now we got to be extra careful here. Notice we have a minus sign. So if we factor or cancel one of these n's down here in this 1 over n cubed, if we knock that down 1 power to n squared, we've got to take out this n to the first and also this n to the first. We need to hit 1 on each side of that minus sign. Now that's going to make our computations, I think, a little easier when we go to FOIL some stuff out. So limits, n will go to infinity at some point. We have 1 over n squared, bracket. Let's see here, we can do a cancellation. Divide by 2, that 2's gone, and this denominator is now down to a 3. So denominator 3. And if we FOIL out the stuff here in the blue ink, we're going to have 2n squared plus 3n plus 1 minus, let's see here, we'll just leave that as, let's see, let's break this into its separate fractions. The numerator n over its denominator 2 plus the numerator piece 1 over its own 2. And now, let's see what happens. We're almost ready to let n go to infinity. We're going to distribute that 1 over n squared. So this n squared is going to distribute to this 3, and to this 2, and to that 2. So we have our limit. N is about to head off to infinity, and we have that numerator was a 2n squared plus 3n plus 1 all over 3n squared minus n over 2n squared plus 1 over 2n squared. That's supposed to be a squared. Now we can let n go to infinity, and remember our little rule for limits out there to infinity, and it's algebraic. Look at that power struggle between the numerator and the denominator. In the first term, it's a tie, so the power struggle is even. That limit is 2/3. Minus here, denominator is more powerful. That's heading for 0. Plus, this denominator is even more powerful, so it's also heading for 0. So all of that work to get 2/3. And again, we kind of made it hard on ourselves by making sure every rectangle's base was a different width. It would have been much easier computationally to do that with even width bases on all of our rectangles. I'm thinking I did not put one of these in the homework, and there will not be one of these on the test. There are easier ways to do these summations. Okay, the worst part of this lesson is over. Now, from example 7 in a previous section 4.2, we know that the region shown in figure 419 down below has an area of 1/3. When we did an integration to the y-axis, we found that area was 1/3, and this was the root of x from 1 to 1. And what we just found here, this region was 2/3. So now that makes sense. If that's 1/3 and this is 2/3, it's a 1 by 1 square. So the area should add up to 1. It makes perfect sense. Ooh, now here, let me see this here. This agrees with the limit we found in example 1, even though that example used a partition having subintervals of unequal widths. The reason this particular partition gave the proper area as n increases is the width of the largest subinterval approaches 0. This is a key feature in the development of definite integrals. When we chopped up our region into subintervals, we had rectangles of different widths. And then we figured out which one was the largest, and the largest rectangle approached 0. As the largest one approached 0, that meant all the smaller ones were also pinched towards 0. If this is defined as the biggest rectangle and we start shrinking it towards 0, then all the other rectangles under it are also shrinking towards 0. Back in section 4.2, the limit of a sum was used to define the area of a region in the plane. Finding area by this means is only one of the many applications involving the limit of a sum. A similar approach can be used to determine quantities as diverse as arc lengths, average values, centroids, volumes, works, surface areas. The next definition is named after George Friedrich Bernhard Riemann. He only lived from 1826 to 66, only 40 years, but his computations to math were huge. Although the definite integral has been defined and used long before Riemann's time, he generalized the concept to cover a broad category of functions. In the definition of a Riemann sum below, note that the function f has no restrictions other than being defined on the interval from a to b. In 4.2, the function f was assumed to be continuous and non-negative because we were finding area. So we stayed above the x-axis, like if we were finding the area from here to here, that area is above the x-axis, so it would all be called, or so-called, positive area. Riemann sums can also dip below the x-axis. There are no restrictions on that. So here's our official definition of a Riemann sum. Let f be a function defined on the closed interval from a to b, and let delta be a partition of that interval from a to b. Now here's how it works. Our left endpoint is a, our right endpoint is b. We start at x sub 0, and that's less than x sub 1, which is less than x sub 2, which is less than dot, dot, dot. All the way over here on the other end, b is equal to x sub n, our last part of the partition. And if we start working left, if we don't know what n is, this would be n minus 1, n minus 2, and so on, where that delta x sub I is the width of the ith subinterval. So here on our right is x sub I, to the next one to the left would be x of I minus 1, the next number lower. And if c sub I is any point in that ith subinterval, then the sum, the summation from the first to the last of our height times our base, comma delta x sub I, or I minus 1 to x sub I. This is called the Riemann sum of our function for that partition. The sums in 4.2 are examples of Riemann sums, but there are more general Riemann sums than those covered there. Now, the width of the largest subinterval of our partition is called the norm of the partition, and it's denoted like this. We have our little delta there, and it kind of looks like those double absolute value bars on there. That is called the norm of the partition. If every subinterval is of equal width, then the partition is a regular partition. And our norm is just our delta x, and we know delta x is b minus a over n. B and a are the endpoints, and n is the number of rectangles we want to divide up into. For a general partition, the norm is related to the number of subintervals from a to b. In the following way. We would subtract b minus a up top, and that would be divided by the norm. That's always going to be less than or equal to n in our general partition. So the number of subintervals in a partition approaches infinity as the norm approaches 0. That is, and let me get my highlighter out, this is pretty important, that is, the norm approaching 0 implies that n is heading to infinity. Because remember, the norm is the biggest partition. As we shrink that towards 0, we're shrinking all of them. That's heading our n value off to infinity. The converse of this statement is not true. Just because n is going to infinity does not mean that the norm is heading for 0. For example, let delta sub n be the partition from 0 to 1 given by this. 0 on the left, 1 on the right, and over here on the left we have 1 over 2 to the nth power. Our next one would be 1 over 2 to the n minus 1 power. As we work our way along, we're going to have 1/8, 1/4, 1/2, all less than 1. And as we see down here in the picture, figure 420, for any positive value of n, the norm of the partition is a half. So as we let n approach infinity, does not allow or does not force the norm to approach 0. So here, if we let this n get infinitely big, we're going to get very, very small fractions in here. But our norm, our biggest base, is still here is 1/4. From 1/4 to 1/2, that is not being squeezed to 0 as we let n go to infinity. So the converse is not true. Just because n goes to infinity, we are not forcing the norm to approach 0. And now we get into definite integrals. And let's see here. I'm not going to read through this. This implies with the delta epsilon definition of a derivative. We've been avoiding that like the plague. It is very confusing. It is nowhere on the AP test, and this class is all about the AP test. So here, we are going to bridge the gap between summation notation, the limit as our norm goes to 0, and an integral symbol. Remember when we anti-derived at the end of chapter 3, now or at the start of chapter 4. Now here's where we're going to make the bridge between the summation notation and the integral notation. We're getting very close to the fundamental theorem of calculus. So if f is defined on the closed interval from a to b, and the limit of the Riemann sum over to partition, the limit as the norm goes to 0, our summation from the first to the nth rectangle, height times base, if this exists, then f is said to be integrable on that interval. And the limit is denoted by this. As the partition heads to 0, the summation from 1 to n of our function times our base is the same as the definite integral from a to b of f of x times dx. Here is our function f of c sub I. We're just replacing that with f of x. Delta x and dx are interchangeable, and this limit of a summation is replaced with the integral symbol from a to b. A at the bottom, b at the top. The limit is called the definite integral of f from a to b. The number a at the bottom is our lower bound, or the lower limit of integration. The number b at the top is the upper limit of integration. Now, it's not a coincidence that the notation for definite integrals is similar to that used for indefinite integrals, and you'll see why in the next section with the fundamental theorem of calculus. For now, it's important to see that definite integrals and indefinite integrals are completely different concepts. Let me get my highlighter out. A definite integral, whoa, that was supposed to be yellow. A definite integral is a number, like 10 or 50 or a million. Whereas an indefinite integral is a family of functions. Don't forget your plus c at the end. Though Riemann sums were defined for functions with very few restrictions, a sufficient condition for function f to be integrable from a to b is that it is continuous on that interval. If we want to see a proof of that theorem, it is beyond the scope of this textbook. You would have to look into a much more advanced math book. So here we go. Continuity implies integrability. If function f is continuous on a closed interval, then that function is also integrable on that same interval. That is, the definite integral from lower limit a to upper limit b of f of x dx does exist. And in this example, we're going to sort of bridge that notational gap. So here it says evaluate this definite integral. We want to go from -2 to +1 of 2 times x dx. Okay, let's start converting this into the other notation that we are more familiar with at this time. Delta x sub I is the same thing as delta x, and that's just b minus a divided by n. And in this case, our b value is 1. Our a value is at the bottom, -2. So that's going to be 1 minus -2 over n. Minus the negative will turn that to a positive. So what we have is 3 over n. And that's our delta x. Oops, I did not want to grab that. Also, let me just rewrite it here. 3 over n. Okay, where do we begin? We need a beginning end point. It's usually nice if we begin right on the y-axis. We start with 0 plus our first I times delta x. You know, we had a little formula there. It was a plus I times delta x. Now here our a value, our lower limit, is that -2 at the bottom of the squiggly. So that's going to be -2 plus I times delta x. Well, our delta x is 3 over n. So that's going to be 3 over n. and then times I. I'm just going to put the I up there in the numerator to keep that 3 company. So there's our left end point, or our end point formula. So our definite integral from -2 to +1 of 2x dx, we can translate into the limit as we send our norm off to 0 of the summation from I equals our first rectangle all the way to the nth, f of c sub I, that's where we use the function to determine the height, times base of the rectangle, delta x. And let's see, I'm going to clear this and slide this other stuff up to about, yeah, whoa. Okay, let's go, here, I'll underline in red, this is still, we're in function notation. Let's actually jump into the function, and we can replace, remember, if the norm is approaching 0, that's the same thing as n going to infinity. So we can swap out the norm to 0 for n to infinity, and then we're going to have our summation from I equals 1 to n. Now our function is 2x, back up here in the upper left corner, that is 2 times x dx. So 2 times x dx. Now in the next step, we're going to take out, I'm going to underline it in red, this x, and we're going to replace it with that endpoint formula that I erased a few minutes ago. And hold on there, we're almost done with all this limit and notation and summation stuff. As soon as we get to the fundamental theorem, we will leave all this in the dust. So the limits, n will head off to infinity at some point. We have our summation from I is 1 to n, 2 times x, but now x is out, and we're going to replace that with the -2 plus 3i over n. And then the dx is replaced with the 3 over n. And there we go. Now, remember, we can pull things out between the limit and the summation. Keep our limit notation. Ed is going to infinity. And we'll have our summation here. Let's see what can be dragged out. We have this 2. That'll be fine. And then times a 3 over n. This stuff in here is an added quantity, and we've got an I in there. We don't want to drag that out because we got a formula for that. So this 2 times 3 over n is 6 over n. And then we're going to have this -2 plus 3i over n. Let's see here. Let's distribute the 6 and the summation, or the 6 over n and the summation, to the -2, and also distribute it to the second term. And we'll just keep our limit notation nice and safe out here. So let's see, I'll do the first one in black ink. We're going to have 6 over n, summation from the first to the nth rectangle of -2, plus, and then we're going to have a 6 over n summation of 3i over n. And remember, that limit notation applies to this whole kit and caboodle. We'll let n go to infinity as soon as we possibly can. Now, before we use our n or our I formulas, our summation formulas, we can, in this second one over here, we've got a 3 over n we can pull out because we just want to leave that I there. So let's see, we've still got our limit, and we'll head to infinity. We've got 6 over n, summation to n of -2, plus, now here, the 3 over n, we can pull out with this. That's going to be 18 over n squared, and then after the summation symbol, we're just going to have the I left. we pulled the 3 over n out front. Okay, we are ready to get rid of the summations and the i's by using our formulas. We still got this limit notation lurking out here. So if I sort of block this off in red, we've still got a 6 over n, but now the summation of -2, remember we just multiply the upper limit with that number, so that is now just a negative 2n. I'm going to put it over 1. And then we've got plus this 18 over n squared. This summation of I, we replace with n times n plus 1 over 2. N times n plus 1 all over 2. Okay, it's just a little more algebra, and we let n go to infinity at our earliest possible convenience. And this nasty example will be over. So let's see here. Probably let n go to infinity in the next step. So this term, the n's are going to cancel, and we've got a -2 times a 6. That's -12, last I checked. Plus, here, this n is going to cancel with one of these. So our denominator here is going to be 2 times n, 2n. And up top, we can distribute the 18. 18n plus 18. Well, we're letting n go to infinity, and we've got a polynomial with, a fraction with polynomials. Let's look at that power struggle between the numerator and the denominator. So this, when we let n go to infinity, that -12, nothing's going to happen to it. Ooh, and also here, these n's are going to cancel, and we've got 18 divided by 2, that's plus 9. This 18 is going to go away because, if we broke that into separate fractions, that would be 18 over 2n, so that is headed for 0. -12 plus 9 is equal to -3. When we were finding other integrals, when they said it was continuous and non-negative, we were always above the x-axis. So all of this area, you could call it positive area. So our answer was always positive. What we found here is a definite integral where some of it was under the x-axis. So this is kind of negative area. And we had some area that was above the x-axis that was positive area. So when we netted the negative and the positive, we ended up with negative area. That means graphically, the area that we found, more of it is under the x-axis. And if we think about it, 2x, that's just a straight line. 2x to the first plus 0 is a slope of line 2 going through the origin. And we went from -2 to +1. So from -2 to 0, we accumulated here -12 square units of sort of so-called negative area. And then from 0 to 1, this was our +9. So -12 plus 9 is -3. We have more negative area than positive. Our definite integral was equal to a negative number, -3. Whoa. Because the definite integral in example 2 is negative, it does not represent area of a region. Definite integrals can be positive, negative, or 0. For a definite integral to be interpreted as area, the function f must be continuous and non-negative. It has to stay above the x-axis. We'll see that in the next theorem. And there it is, theorem 4.5. The definite integral as area of a region. So if f is continuous and non-negative, that's key, on the closed interval from a to b, then the area of the region bounded by the graph of f, the x-axis below, and the lines x is a and x is b is seen here. So let's tie the graphical representation to our integral. Area, we're going from a to b. A is the lower limit. B is the upper limit, so those are numbers on the x-axis. F of x is our function. That is our upper bound. I'm highlighting in red here. And then x-axis will be below with respect to x. So we're finding the area between the lines A and B above the x-axis but below the curve. So to be considered area, we must be non-negative. I mean, if we dip below the x-axis, we're going to have a negative area accumulation, so to speak. All right, as an example of theorem 4.5, consider a region bounded by the graph of this, 4x minus x squared. That's going to be a downward opening parabola. And the x-axis will be our bottom boundary for that. Because f is continuous and non-negative from 0 to 4, as we see here in the picture, downward opening parabola will hit at the origin and hit at x is 4. So if we wanted to represent this area in the form of a definite integral, we are non-negative between 0 and 4. So our lower limit and upper limit, 0 to 4. And then here is our function, 4x minus x squared, our downward opening parabola with respect to the x-axis. So that represents that area. So a straightforward technique to evaluate a definite integral such as this will be discussed in the next section. For now, however, we can evaluate a definite integral in two ways. We can either use the limit definition with a lot of algebra, or we can check to see whether that definite integral represents the area of a common geometric region such as a rectangle, triangle, or a semicircle. Think back to geometry class. So here we go. Sketch the region corresponding to each definite integral. Evaluate each integral using a geometric formula. So let's look at this first one. We see from the upper and lower bounds a 1 at the bottom, a 3 at the top. So we are going to go from 1 to 3 on the x-axis. And then our function is right here. Y equals that. So y equals 4. How do you graph y equals 4? Well, that's just a horizontal line. 1, 2, 3, 4, and we go straight across. So the region that we're looking for is bounded on top by that black line. The x-axis here in blue, and I'll also use blue for the line x equals 1 and x equals 3. So what's our common shape? It's a rectangle. Area equals base times height. Our base, 1 to 3, well that's 2, times the height is 4. 2 times 4, last I checked, is equal to 8. Okay, common geometric shape. Here's the much better graph from the book. There we go. Up next, we are moving along the x-axis from 0 to 3. And let me move this down here a little bit more. Whoa, get down there. Get. There we are. Okay, y equals x plus 2. That's our function. Y equals x plus 2. So y-intercept of 2, and then our slope is 1. Up 1 over 1, up 1 over 1, up 1 over 1. We're going from 0 to 3. 1, 2, 3. So let's find the height of that. When I plug a 3 in here, 3 plus 2 is 5. So 2, 3, 4, this will be 5. And that will be the height of our function there. So the line x plus 2 is this blue line. We are bounded below by the x-axis, and we've got the line x is 0, and we've got the line x is 3. Now you could chop that into a rectangle plus a triangle and do two area formulas and add them together. Or if you tip your head 90 degrees, you'll see that that is a trapezoid. The area of a trapezoid is 1/2 the height times the sum of the bases, base 1 plus base 2. Remember now, the bases are the parallel sides. So here, these red sides are the parallel sides. These are the bases. So this base, the shorter one, that's a height of 2, plus this base, height of 5. We already figured that out. The height, this is the distance between the parallel sides. So this distance is the height of the trapezoid. If we rotate our head 90 degrees counterclockwise, we see that height is 3. 1/2 times 3 times 5. That turns into 21 halves, or 10.5 square units. The area of that trapezoid, 10.5 square units. The last one, root of 4 minus x squared from -2 to 2. So we're going to go from -2 to +2. And if we plug a 0 in there, 4 minus 0 squared is the root of 4, or 2. If you haven't noticed it yet, this is going to be a semicircle. If you see a radical with a number minus x squared, it's going to be a semicircle. If it's a positive radical, it'll be the top half. And the number that comes in there first, that is radius squared. So if we square root that, it's radius 2. So what we have is a half a circle, radius 2. We have a formula for a circle. The area of a circle is pi r squared. So for a semicircle, cut it in half, 1/2 pi r squared. And we've already identified the radius is 2. So our area is 1/2 times pi times 2 squared is 4. Half of 4 is 2. So that's 2 pi. 2 pi, or approximately 6.28 squared units, whatever those units happen to be. So again, we can avoid a lot of algebraic computations for a definite integral if we can identify that it's just a common geometric shape. See, now here's the book's trapezoid, and then their semicircle, a little better than mine. Okay. Now there are some properties of definite integrals. The definition of a definite integral of function f on the interval a to b specifies that a is less than b. Remember, a and b are numbers on the x-axis. So a is always going to be the lower number, b is always going to be bigger, so it's going to be to the right of a. Now, however, it's convenient to extend the definitions to cover cases where a and b are equal, and also where a is greater than b. Geometrically, the next two definitions seem reasonable. For instance, it may, we'll get to that here in a second. Oops, whoa, that was an accident. There we are. If f is defined at x equals a, then the integral from a to a of f of x dx is always equal to 0. So think about it this way. If these numbers are the same, a to a, no matter what this function is, it does not matter. It's always going to equal 0. Because remember, these numbers represent as we move along the x-axis. If I go back to here, if we were looking at this trapezoid, and let me change the trapezoid numbers from 2 to 2. It's like we draw one side here of the trapezoid at 2, and we draw the next one right on top of it. So it's not even really a trapezoid. It's not a geometric shape. It is one line that we can make infinitely thin. And when it becomes infinitely thin, its area is 0. So if you see the top and the bottom numbers are exactly the same, this function does not matter. We have accumulated no area. The answer is always going to be 0. Now this next one here, number 2, notice this here. If the b and the a are backwards, what we are allowed to do is switch these. I can move a to the bottom, where it's supposed to be, and I can move b to the top, and I'm going to leave the function alone, but to allow me to make that switch, I'm just going to put a negative out in front of the integration symbol. So you can flip your upper and lower limits if you put a minus here. Now do not confuse this. We can factor numbers out. If we have -2 times our function f of x, we're allowed to factor that -2 out because it's a constant multiple. If you factor a negative out, you do not switch your upper and lower limits. This is just made for some convenience if you feel that you want to switch your limits. If you've got a here and b here of f of x, you just put a negative here and switch your limits places. The b and the a will switch places. Do not confuse it with factoring a negative number out of your function. And here we go. This would be a great one on the AP test. Here is our definite integral symbol. We're going from lower limit pi to upper limit pi. As soon as I see that, I should have alarm bells going off in my head. It doesn't matter what this function is. In this case, it's just sine of x dx. That is equal to 0. When the upper and lower limits are the same, disregard the function. Your answer is 0. Now this next one here, example 4b, this is kind of a setup or a play from here, example 3b. So here, I'm just going to steal this and put it over here. Yeah. Oops. Get up there. Notice that these are just, oh, where's my mouse? There we go. Now, this is our new example 4. So if we look back in example number 3, the integral from 0 to 3 of x plus 2, that was equal to 21 halves, or 10.5. What they're asking us for here in example 4b, I'm circling here in blue, is the same thing, but they've just switched the limits. Now the 3 is at the bottom, the 0 is at the top. So to compensate for that, we're just going to put a negative in there. Now the answer is negative 21 halves, or negative 10.5. So switching your upper and lower limits, you just negate that answer. Okay, what's in store next? Ooh, additive property. If we have two integrals that are adjacent, we can just add those separate pieces together. Let me make this a little bit bigger. If f is integrable on three closed intervals determined by a, b, and c, then let's go over here on the right first. We're going from A to C first, and then that one leaves off at C, but this one picks up at C and finishes off going to B. So that C is sort of a bridge in the middle. So we can combine those to one integral that goes from A at the bottom all the way to B at the top. And it's easy to see what's going on here graphically. Oop, there we go. So here we're going from A to C is our first area. I'm going to sort of highlight that here in blue. And then we're going to pick up at C and finish going all the way to B. So that I'll highlight here in red. We can combine those into one definite integral starting at A and going all the way to B of f of x dx. Because remember, what we're dealing with here are lines which are infinitely thin. So this line C is infinitely thin. It has no area. So we can add from A to C together with C to B and get one big area all the way from A all the way to C. It kind of just makes sense. Who says calculus is tricky? So we're going to use here in example 5 that additive interval property. Now this one, it might be best to think about it graphically. We are going to go from negative 1 to 1 of the absolute value of x. Negative 1 to 1, absolute value of x. We could just plug in some y value or x values. If I put x is negative 1 in there and I absolute value it, I get a y value of positive 1. Remember, the absolute value of x is going to sort of look like a v graph. So this is part coming down. And then after 0, if I plug in absolute value of positive 1 is also 1. So we get our V-shape graph. Now we're going to accumulate the area starting at negative 1 and go along to here. And then we're going to go from 0 and accumulate up to positive 1. So what they want us to do here, we're going to break this kind of into two integrals. We're going to go from negative 1 to 0 of the function negative x dx. That is our first triangle. And then we're going to add to that 0 to 1 of positive x dx for the first quadrant triangle that we have there. And I don't want to erase my awesome picture. So here, let's just say, these are two triangles. This is going to be our first triangle, 1/2 base times height. Plus, I'll switch to black ink, another triangle, 1/2 base times height. And these two triangles are very, very similar. Our first triangle, base here is 1. Height is also 1. Plus another triangle, 1/2. Triangle base here is also 1. Height is also 1. So that just becomes a half plus a half, or 1 square unit. No calculus required. We used the calculus notation and just identified the geometric shapes and let the geometry take over. Now, there are also some other properties of definite integrals. You've seen similar properties with limits and derivatives. You know, I've said before in class that these properties echo all throughout calculus. Because the definite integral is defined as the limit of a sum, it inherits the properties of summation that we saw back in the book on page 291. So the first one is the constant multiple rule. Definite integral of k times f of x dx. K is a constant. We can factor it out. We have the additive property, or sums and differences here. We've got the integral from a to b of f of x plus or minus some other function g of x. We can sort of, in essence, just distribute the integral symbol. So the integral from a to b of f of x dx plus or minus another integral from a to b of g of x dx. So we can, just like we derived individual terms of polynomials one at a time, we can also integrate individual terms of polynomials one at a time. And let's apply some of these properties here. So they're giving us a property here up top. I'll underline it in red, in red. And then down here, sort of like a map has a key, they're giving us these little components, keys. The integral from 1 to 3 of x squared is 26 thirds. The integral from 1 to 3 of x dx is 4. The integral from 1 to 3 of dx is equal to 2. So what we're going to do, this part up here underlined in red, we're going to break that into component pieces and then evaluate each piece separately. So first, let's kind of distribute that integral symbol. So we're going to go from 1 to 3 of negative x squared dx. And then we're going to go plus definite integral 1 to 3 of 4x dx minus the definite integral 1 to 3 of just 3 dx. Now let's look at our key. We're pretty close. Here we've got in our key x squared dx, but down here we've got a minus x squared dx. So in this, to make it match the key perfectly, let's factor out the negative. Negative integral 1 to 3 x squared dx. Plus, we have in our key an x dx. You know, here we've got a 4 x dx, so we can factor this 4 out. So now that's 4 definite integral 1 to 3 of x dx minus, you notice here the last piece in our key, we just have a definite integral of dx, or a 1 dx, so let's factor this 3 out. Minus 3 definite integral 1 to 3 dx. So now we've made the problem we've broken up very similar to components in our key up here. So we can do some substitutions. I will block off in black what we're going to swap out. So this is in our key. Don't lose track of this negative out here. We'll bring that negative along. And what I blocked off here, that's equal to 26 thirds. So that's a negative 26 thirds. Plus this that I'm blocking off is going to be replaced with a 4. But don't lose track, we have this 4 out here, so that 4 that we factored out is going to be multiplied by the 4 that we replaced the integral with. Minus this integral 1 to 3 of dx is going to be replaced with a 2. So we've got a minus 3 times that 2. And then if we turn all those into, we'll turn them all into thirds. We'll keep our negative 26 thirds plus. This is 16. 16 times 3 is 48, so that's 48 thirds. And this is 6 over 1. 6 times 3 is 18, so that'll be minus an 18 thirds. And if we add up all our numerators, we get 4 thirds. And there we go. It looks like here we've got a graphical solution There's our original function, and we're going from 1 to 3, so that's where that parabola bumps above the x-axis. So we could determine that definite integral has a value of 4/3 with the calculator, but that's not near as much fun as we just had here. So we'll put the calculators away. Okay, integrating a function with a discontinuity. So let's use the graph on this one. So evaluate 0 to 5 f of x dx, where our function is piecewise. -2 to 7, or -2x plus 7 if we're less than or equal to 3. And then beyond 3, it's equal to 4. So, our transition number is at 3, and that 3 is in between 0 and 5. We could graph these and figure out what they look like. 2x minus, or -2x plus 7, that's a line slanted down. 4 is a horizontal line, but it's going to look like this. Now let me make that a little bit smaller. So let's see. This integral, I'm not going to copy it down, 0 to 5 of f of x dx. We can break that into two smaller integrals. Let's see here. We can do one integral from 0 to 3, the transition number, 0 to 3, and that's just going to be the top piece of the piecewise, -2x plus 7 dx. And then we got some more area, so we're going to add another integral, and this one starts at 3 and goes to 5, 3 to 5, and that's just going to be 4 dx. So our common shapes is a rectangle and a trapezoid. Let me move that a little bit down there so we can see it. So the first one here is our trapezoid, and the formula for a trapezoid is going to be 1/2 the height. The height is the distance between the parallel sides, so that's here, this red line. That's 3. And then in here we do the sum of the bases. Our first base goes all the way up here to 7. Our next one just goes to 1. So 7 plus 1. And then we've got our other integral, and that is just a rectangle. Base times height, that's going to be base is 2 times the height is 4. 4 times 2. If we compute that, we are going to get 20. That turns into an 8. This will turn into a 12. Very nice. Okay, we're almost done. I think I'm done with examples. Just a little more reading here. If both f and g are continuous functions on a closed interval from a to b, and f is always in between g and 0. So think about, g is always the biggest, and f will always be underneath. So if we graph it, that means the g function is always on top of the f function. So that's true for all values between a and b. Then the following properties will always hold true. First, the area of the region bounded by the graph of f and the x-axis must be non-negative. Second, this area must be less than or equal to the area bounded by the graph of g and the x-axis. So think about that. The area under g always is going to be more than the area just under f, because g is always on top. It just makes sense that the area under g will always be more than the area under f. So here is the area under f is always less than or equal to the area under g. And then the area under f is always non-negative. Because we are above the x-axis, the area under here is always going to be positive area. Again, because we are above the x-axis. Okay. And this starts where the book would introduce the trapezoid rule. I have a separate video and a handout just on the trapezoid rule, so you can check that out for the extra credit available in the third quarter. And I'm losing my voice. I need a cup of tea. This is a great spot to stop the video. Next time we're together in class, we'll try some odd problems.